Good afternoon, good evening, wherever you are, whatever you're doing. Welcome back to the channel. And today I'll look at using recursion to generate state matrices. So to crack on, we're using recursion, so the recurrence or continuing a pattern to find the state of something after nth times that it happens. So it'll have an initial state, something will happen to it via the transition matrix, and then state number one, or the first application of the transition matrix, will give us state number one. So what does this look like and what does it mean? So in this example, the factory has a large number of machines. The machines can be one of two states. They're either operational or broken. Broken machines are repaired and come back into operation, and so on. Okay, operational machines become broken. At the start, 80 machines are operational and 20 are broken. Okay, and we're asked to use this recurrence relation to answer some questions. Now, just to annotate these a little bit, so we know that these here are the operational, these here are the broken, so we're told up the top. But with the transition matrix, just to make that a little bit clearer on what is what, if we were to line the operational and broken machines up here as a matrix, you can see that 80 here lines up with this row. So this is our operational rows. And so this is our broken rows. Okay, so first row, second row, and we can apply that to the columns as well by putting first column, second column as well, okay, to match the first and second rows. Okay, so just to make that a little bit clearer, so we can see here that means that out of all the machines that are operational at any point, 85% of them remain operational. If I just put a line through that, so here's our operational machines currently, and then by the end, they stay operational. The operational machines that become broken are 15%, 0.15, okay, line up with the broken. So this is now, and then later. Alrighty, so hopefully that clears up what that looks like. Anyway, we're told that we're given a recurrence relation here, and we want to use that to solve some problems. So determine the number of operational and broken machines after 1 and 3 days recursively. So question number 1 asks us to do this. We've got SO. I'll write this one out in full. So SO is equal to 80 and 20, so we've got 100 machines in total. And then S0 plus 1, okay, because it's the initial matrix, the first one we've got to work with, is equal to 0.85, 0.15. So just rewriting the transition matrix. And that is all multiplied by Sn. So Sn's whatever matrix, whatever state we're currently in. We're currently in state 0. So we multiply that there. And at the end of it, that will give us S1. Okay, because S0 plus 1 is equal to 1. Over here, I've already typed in the matrices to start with. I'm going to put, so that I can repeat the process quickly, I'm going to put S and that. Then I'm going to hit T for our transition matrix and multiply that by my answer. That allows me to now just hit XE over and over again to get a repeated answer. So there's S1. So S1 is 69 and 31 machines. Okay. And then day 3, after 1 and 3 days recursively. So day 3. So day 3, we're going to start with, we would take S1 and add 1 recurrence to it, which is an application of the transition matrix. So we're going to do T times 69 and 31. And that'll give us S2. So over here, we can go that is S2. And then I'm going to hit it again just to get S3. Get it all out of the way again. So S2 is equal to 60.2 and 39.8. And then S3 would be S2 plus 1, which is T times 60.2 and 39.8. Okay, so after that, S2 becomes 53.16 and 46.84. So that's S3. So after, if we want to answer this in full again, you can't leave these things in their matrix state. So after 1 day, we had 69 operational and 31 broken. 69. And then after 3 days, there were we'll just round it to the nearest whole machine. There were 53 operational and 47 broken. Okay. Number 2, determine a rule for the state after n steps and calculate the broken and operating machines after 10 days. Okay, to determine a rule, I'm just going to cut off pieces here. Don't have a lot of page left today for some reason. Okay, so number 2, do a different color. Determine a rule. Our rule for any state is Sn is equal to Tn times S0. Okay. So we can apply that. So to write out the rule in full, we would want Sn is equal to the state matrix, sorry, the transition matrix to the power of n, and that's equal to, not equal to, and that is multiplied by S0, which is 80 and 20. Okay. Now we want to find out S10, I believe, yeah, S10, 10 days. So S10 is equal to T to the power of 10 times 80 and 20. Jump over to our CAS and give it t power of 10 multiplied by s. Our answer to the nearest whole machine is 31 and 69. Okay. Again, if you were asked to answer that question, you would need to take it out of the state matrix. So these are our operational and these are our broken machines. Okay. Last question gives us estimate the steady state of broken and functioning machines. So this is where we have to come up with two consecutive powers to which we apply to the transition matrix and the number of machines in the operational and broken state are steady for the two. Okay, so generally you pick a relatively high number. To be honest, looking at that, I'll start by picking an n value of 10. So let's try when n equals 10, 10, not 10. I will be picking n equals 20 to start with, and n equals 21. So let's go over here. I might just copy this down. So n equals 20 and n equals 21. So there we can see to the nearest whole machine, we look like we have a steady state. Actually, no, to the nearest whole machine, this would round up to 26, and this would round to 26 as well. So that rounds to 26. That rounds to 26. I'm skeptical because this is going up. So I reckon if I go one more, let's go up a couple more, 25. And we are rounding to just getting closer to 25.5 and so on. Actually, sorry, that was meant to be. There we go. So 25 takes this to rounds to 25, and this rounds to 75. So if I try now for t, put a mark next to this, so I know that these two weren't quite where I wanted them. So I could see that 20 and 21, that because this has gone from 0.63 down to 0.50 or 0.51, that it was likely to keep going down if I went a few more states up. So going from 25 to 26. Should hopefully give me, so it's going to 25 again. So I've got a steady state there where my numbers appear to be leveling out. To be honest, I'm going to go another one. I'm not quite happy with how much they're jumping at the moment still for its state. I'm going to go, let's go 50. Okay, and then go 51. Okay, so now you can see that that is settling on 25 well and truly. So we've gone really small increments now from there to there. So now I'm happy with that. I'm going to say that I've used n equals 50 and n equals 51, and my state matrix is settled on 25 and 75, and so be it for 51 as well. So the steady state of broken and functioning machines would be that there would be 25 functioning machines and 75 broken machines. Okay, so hopefully that helps out. I know that can be a long process, but if you're not confident, just pick a larger number once you get up to the 50s sometimes. Or the larger the number, the more accurate you'll be. Hopefully that explains the steady state matrices. And if you have any questions or comments, pop them down below. If you like the video, give it a thumbs up. And if you need more of this type of thing, then subscribe so that you don't miss the stuff coming out. Hopefully that is all good. Have a beautiful day, guys, and I will talk to you again soon.